from the reading, they mentioned about in Z15 the cyclic group 3. So we want to be able to figure out what 3 is going to be. So you're just writing down the set in Z15 that 3 goes to. So first of all, you have 3 all by itself. That's where you're starting. And Z15, is that addition or multiplication? Addition. So 3 plus 3 would be what?
6.
6, all right. Mod 15. And then add 3 to that and you get what? Add 3 to that. Add 3 to that. 15 becomes?
0.
0. If you add 3 to that, you're back to 3. So it is actually the set, I'm going to put 0 at the beginning. 3, 6, 9, 12. That's our cyclic group of 3 in Z15. Question?
Is there any way to denote that we're in Z15 in your answer? Like generator with the
Mod 15, if you want to. If it's not completely understood, but that's how you denote modular. You kind of put it as a subscript.
What do you do? Put it on 3?
Yeah, you can put it on the 3 here. This.
Or
Yeah, you guys are actually used to this notation. Let me just let you use this notation.
That was like more work.
It is way more work.
Brody.
I just was curious.
If you want to put it, if you want to use that notation, but that is a notation that we have used in other
So
classes.
the notation 3 modulo 15 would be inappropriate.
Well, that's just for the 3. I mean, I have to put it on the 3 too.
But can you just do the 15 without the brackets? Would
Yeah.
you have to put the 15 on the 3 where you're at right now without the brackets?
If you're going to have it in here, then you should have it out there. You should have it on all your numbers.
So would we be kind of off if we just have numbers, no brackets, and no subs?
Your book doesn't use little numbers on it. So no, I wouldn't count you off on it. Your book doesn't use that notation. In this case, they use the notation interchangeably. So you are trying to find the cyclic group of 3 mod in Z5, and then the cyclic group of beta in S3, which was something they also mentioned in your book. So part A and part number 2 are stuff that they mentioned in your book. I threw in part B here just to see what the difference is if you change the group that you're in from Z15 to like Z5. And we're going to compare them. But go ahead and start working on that. And let me know when you get done, because I know that's not going to take long and I probably won't make it through to see. I can't remember who's on it, but it shows a guy, he's doing a dance routine, 2 guys doing a dance routine, and one guy is supposed to be kind of singing to a mic, and so he holds the mic clear out here when he's singing, and he'll do things like bring it over to his face and clear his throat and stuff like that. Kind of like me, I'll record you guys when we're not doing anything. I'll shut it out when you want to know what's going on. Yeah. Okay, so let's try to do this one. First of all, what do we get? We're starting with 3, right? Add 3 to that and you get?
4.
Yeah, that becomes 6 mod 5 becomes 1. Add 3 to that and you get? 4. And we're gonna get to 0. Add 3 to that and you have 7. Mod it by 5 and you get 2. Add 3 and that goes to 5. Mod by 5 goes to 0. For the order, yeah. So then let's do that. Order of 3 in Z5 is what? I tried to make that. You have to start with 3, which means we're going to have to fix yours on that one because we didn't count it right. You start with 3. So you have 3, 1, 2, 3, 4, 5. Yeah, so you had it right at first, but then we weren't sure about it, so we changed it. Yeah, I wasn't, remember? That's what you get for being the first student in my office. I second guessed myself. Okay, so you found the cyclic group for B, for beta in S3, right? You guys verified all of that? Did you guys get that to work yet, or were you not done with that? I think some. We'll finish, I'll let you finish that in a minute. What I want to do is look at number 3 right here. Find the order of each element in the group Z2 cross Z3. This should not say subgroup, it should say cyclic group. So let's look at this one. What are the elements in Z2 cross Z3? Let's write that down first of all. Yeah, 0 mod 2 and 0 mod 3, right?
Yeah.
And then 0 mod 2 and 1 mod 3, and then what?
0. Do we have to like look at mod?
I am for my sanity, you don't have to. And then we start with 1. So we have 1 mod 2, 0 mod 3, 1 mod 2, 1 mod 3, and then the last one. So let's make our table. We're going to have 1, 2, 3, 4, 5, 6 rows, so let's make that 7 rows, 2 columns. And this is AB, and this is going to be the order of AB. So the first element we're looking at is going to be the zeros. I got that one. What's the order of the identity? 1. How about the next one? Zero is going to always stay at 0, right? So when you think about it, let's do this one. If you were looking at this, oh, that didn't work. If you look at this in this form, let's write down what it is. You're going to have the original one, and then you add 1 to both of them because that's our generators. So if you add 1 here, and 2 mod 3, right? Sorry, 0 to the 0. No, you're so right. And then what do we get? 1 more? Yeah, 0 mod 3. That goes back to the identity. So how many elements were in here? 3. So what's the order? 3. So tell me about the next one. Zero is going to stay 0 the whole time. You have 2 plus 2 goes to 4. Mod 3 is 1. Plus 2 is to 3. Mod 3. So how many times? 3. Look at the next one. 1 mod 2. 0 for the second one is always going to stay 0. 1 mod 2. How many times do you have to operate on that one to get it to go to 0? Twice. And then the ones. It's twice for the first one, but how many times for the second one?
So
3.
6.
6. You guys all see that? Least common multiple. You can list them like I did for the first one. But I didn't want to list that one. I didn't want to list 6 of them. Getting lazy. How about this one? 6. So there's the order of each element. Notice that in this case, our group Z2 cross Z3 has an order of 6 also. It's the order of, we have elements down here that have order 6, the same order as the group. The question is Z2 cross Z3 a cyclic group? Needs one generator for all of its elements.
No.
Yeah, it will. But it won't under one condition. But I'll show you. Notice what you have here. We could take our 1, 1 here. If you add 1 to itself, you'll get 0. And that will give you our 0, 2. You'll add 1 to itself again, and you'll get 1, 0. So let's actually write out the whole.
Just the fact that we found one element had an order of 6, which is how many elements the thing has.
I'm not sure that theorem's are familiar yet. Let me puzzle on that one for a minute, but I know where you're going. Just because you have an element of order 6, yeah, it is. It has to go back the other direction. Yes. Because, think about it, you can, I'll show you. While we're walking through this. So this is, oh, I didn't want 0, I wanted 1. Watch what happens. Let's start listing these. Of course, the first one we can write down is, I'm going to copy and paste, is going to be 1, 1. You add 1 to each of those, and you're going to get what for the first one? 0 and 2. You add 1 to that one, and what do you get? 1, 0. You add 1 to that one, and what do you get?
0.
You add 1 to that one, and you get? And then you add 1 to that one, and you get? 0, 0. Notice when you're writing these elements down, they are all different elements. So if you know your group has only 6 elements in it, and you know you take an element and you can operate it by itself 6 times and get different elements each time, you know that each of those has to be one of the elements in your group, so you have to be able to make a one-to-one pairing with the elements. Does that make sense? It might not be in the order of the group, but because you can find an element whose order is the same as the order of the group, then you know it has to generate your group for a finite group.
1, 2 also be a generator?
Yes. Could be a more entertaining one. 1, 1 was an easy one to figure out.
Well, and then, because if you came to the same element twice, if you repeat an element, that would mean somehow skip the identity with it.
Yeah. Or
Is that
that you
possible?
went by the identity and then came to another element, so you started a repeat earlier on and didn't notice it. One of 2 cases, no, you can't skip the identity and go back to another element. Yeah. So in this case, our answer is Z2 cross Z3 is cyclic. And we found the generator for it to be a generator. You can have more than one generator.
Just because an element doesn't have an order of 6 doesn't mean it couldn't be a generator, right?
No, it can't be a generator then, because it means that when you operate it on itself, you're
Oh,
you're
yeah,
going to
yeah,
have
it
less
goes
elements
straight
in your full
to
group.
It goes straight from the element back to the cell.
Mhm. Okay, keeping this in mind, Yeah, we're headed on to number 4 now. Where's number 4? Oh, number 5. Somehow we skipped from 3 to 5. Yeah.
You said that you want to also generate.
Yes. So we could actually, where did I write that? You could also write it this way. Notice something that you're looking for your generators in these groups. Numbers that are relatively prime to the modulus of the group. That's what's going to be your generators. 2 is relatively prime to 3, so it can generate your whole group. In Z6, 2 and 3 are not relatively prime, so it can't generate it, but you can use 1 or 5. Your generators are the numbers that are going to be relatively prime. Yeah. Now, before we go look directly at number 5, well, number 4, what we're going to do is do one thing in between. We're going to consider this group. Z2 cross Z6. We want to know if that one is cyclic. So look at this one, and you guys tell me what the we're going to do 1 mod 2, and what is something relatively prime? Someone said 5. Okay, so calculate that and see what you get. What values do we have in this set right here? Is that? Yeah, 1 and 5.
That's my sort of guess.
That's you're done for today, right? And so then what would be another one if you add 1 to 0 and add 5 to 5 and you get 10. Mod 6 comes down to 4. Now add 1 to 0, you get 1. Add 5 to 4, you get 9. Mod by 6, 3. Yeah. Now add 1 to 1 and you get 0. And add 5 to 3, you get 8, which goes to 2. Add 1 to 0, you get
1.
Be careful, Austin. I will type what you say. Add 5 to 2 and you get?
6.
Yeah. 5, 2, 7, 1. Yeah, it comes down to 1. Then what? 0, 0. And then if you add it again, you should get here. Now, how many elements should we have total? 12, right? Do I have 12 here? No. What's happening? That one didn't work. Yeah.
Because 2 and 6 share a common factor.
2 and 6 are not relatively prime to each other here. Therefore, any generators of 2 are not going to be your generators in 6. They're going to not generate everything in that second group. It's not cyclic. When these guys are not relatively prime, it is not going to be cyclic. Always. For you to have a cyclic group, those two numbers have to be relatively prime. So we could have,
You define relatively prime.
they share no common divisors other than 1.
Okay.
So, yeah, what would be a number relatively prime to 10? 7, that's a prime number. How about a non-prime number?
5.
No, because 2 goes into both of them. 9. 9 works. See, 10 is 2 and 5, so you could pick a 3 and a 7. You could say 21, or 3 and 3, you get a 9, or just 3 by itself. Some number. They don't have to be prime numbers, but they have to not share any common factors other than 1. So they have to be relatively prime. Now, let's start looking at, we're gonna stop at 3 and look at one of your homework problems you're gonna be turning in today. Because I've seen a lot of misunderstandings of what the book is asking. So, we're gonna do one in class. But, this is on page 117. And I want you to look at number 1 now. You should be able to look at number 1. Number 1 and number 2 are the same thing. So get in your groups and play with number 1 for a few minutes. I'm going to type up number 1, the statement, so that we'll be ready to prove it after you play with it for a few minutes. E1, number E1.
You don't want to do some homework problem?
No, these ones are important for the test, and I didn't want to assign a ton of homework, so we're doing these so that you'll be able to study them for the test.
Pretty cool.
Yeah, no, this is an important example for the test, so.
Pretty cool. What's that? I know.
Doesn't it?
It's true.
After all the work we just did, it should make some sort of sense.
This makes sense. Just delicious.
Proof by intelligence.
It has the blue box too.
It's obvious.
Can we use, like, can we do a proof that A, comma, 0 is a generator?
If you don't need to say a comma 0, but you should be able to establish the generator.
Because it's a G is a subgroup of G cross A.
No, it's part of the group of G cross H. It's not a subgroup because G cross H is, I know exactly what you're thinking. It's all of our G, H, G is in G, H is in H.
But G comma 0 is a subgroup of that.
Yeah, but that's not the same thing as G.
Right, but we can prove that it,
So what you have to do is you have to say, for all G in G, there exists an N in the integers such that A to the N is equal to G. That's what you're trying to do. Does that make sense? Where A is a generator, A comma B is a generator for G cross H. But you actually get it from the fact that you
Right,
just
yeah,
only
you
have to
just
read
say
it off
that.
the first element, the first part of your point.
right.
Yeah. So it is just a little 2-line. Once you recognize that.
Yeah,
Mm-hmm.
because it's the same end that goes for G cross A.
Yes, that's exactly right. That's exactly right. Oh, I did it again. Told you.
It feels like stupid.
Yeah, it's so hard pressing Control
I
T.
hate that. It's so
Control M, when you guys are not connected to the projector.
Yeah, I see. It's
Control
C.
M. No, what I figured out the reason why after, I don't know, 2 years of doing this. Now, I know the reason why. Because my recording software uses Control M to put markers in.
So
It's
you
a
got-
shortcut for the recording software, so it,
You ended up with a bunch of markers on top.
yes. And I, a whole bunch in a row, I was like, why did I do that?
You ended up with a bunch of markers with the pencils and things.
No, they weren't, unfortunately. That is It's even a funnier joke than you think because a pencil has a definition in mathematics. It does. I am not exactly sure what it is, but it has something to do with a set in geometry. But I really don't have a background in geometry, so I don't know. I just know that a pencil is.
What is pencil? Well,
Jacob will tell you.
that is the way over.
It has to do with inscribed circles.
Okay, have we figured this one out yet, guys?
Pencils.
Yeah, we got off on pencils.
Since AB is
Okay.
a generator for G cross H, and for some N in the
Okay, you're
natural
talking
numbers-
faster than me, so keep talking, but I'll get there. But you're right on to it.
For some N in the natural numbers, A to the N, column B to the N is equal to AB.
Okay, so I'm gonna word this way. Then let G be in. That did not work. G be in our group G, and H be in our group H. Then you said for some N in the naturals. Well, actually, it's in the integers. We know that G comma H to the N, right, is equal to, oh wait, AB to the N equals G comma H to the N. There you go. That's what you were saying so far.
Equal to GH to the N.
Well, now all we have to do is know what AB to the N is equal to. Let's just apply that in between step. That's A to the N, B to the N, and then you have your conclusion, right? Uh-huh. What does that tell you? G
Well-
equals A to the N, and H is equal to B to the N. Thus, A is a generator for G because our little g was an arbitrary element. That makes sense?
The generator of G, not just the generator.
Nah, yeah.
So the generator could be making electricity.
Yeah, it could be. We hope it's generating electricity, yeah. So A is a generator of G and B is a generator of H. Once you find the generators, then you know something. Oh, they didn't ask for cyclic. They just said show it's a generator. Question?
So this works for negative integers?
Yeah. Doesn't matter the power as long as it's negative or positive. Then H has some negative or positive power. It has to be integer power. It can't be roots.
So
Yes.
this is under addition, you can also look at subtraction.
The powers can't be imaginary, but your numbers could be imaginary. Say that one more time.
So this works for addition, you want to subtract.
Subtraction we have defined as being the inverse of addition. So it does by definition of inverses. Mm-hmm.
Generate.
Because we assumed we know chapter 10 now.
We can have like.
Yeah, we're done with that painful experience.
Oh, okay.
We know what our exponents do now. Yeah. Any other questions on this one? You were going to say
Is
something.
that so? Through the inverses, you could generate something backwards by just subtracting things.
Yeah, that's exactly right. Now, if you look at the question in your book for number 2, E number 2, there is no difference other than how it's worded. If you want to show that something is a cyclic group, you just have to find a generator for it. So number 1 and number 2 are the same. You can say number 2 follows directly from number 1. Number 2 says that if G cross H is a cyclic group, then G and H are both cyclic.
So you could literally just say, look at number 2 group wise.
Yeah, don't say look, follows directly is what you could say. So, I hit the Windows key instead of the. So let's do this one is E number 2. Let's write it down. If G cross H is cyclic, then G is cyclic and H is cyclic. So, by E1, there exists an AB, I'll put it this way, AB in G cross H, such that G cross H is equal to AB. It's a cyclic group of AB. Since A is in G and B is in H, by E1, this is where I need E1. This is by definition up here. And then by E1, G is equal to A and H equals to B, because that's what you proved in E1. Therefore, G and H are cyclic. And we'll try not to give you a proof that is that easy on the test, because more than likely, you'll get stumped. You'll think there's more to it than that. So you will not have one that is that short on the test, but I could combine 1 and 2 together. And you could have 1 and 2 combined on the test. Now, number 3 says, show that the converse of this one that we just proved is not true. Can you come up with a cyclic group G and a cyclic group H so that G cross H is not cyclic? Yeah, where the Z mod 2 and the Z mod 4, they're not relatively prime. The cross product, your direct product, is not going to be cyclic. So,
what exactly is the converse statement?
no, the converse is your conclusion implies your hypothesis. Not would be contrapositive. Inverse is not and not. Contrapositive, not switch places. Converse is your conclusion implies your hypothesis, so you're just switching the places. So if G and H are cyclic, so you said Z2 cross Z4, or Z2 cross Z6, the one that I put up earlier. Either one works, because they're not relatively prime. If they're not relatively prime, then you will not be able to get a generator for it. And we saw that already. We played with that already. Now this brings us to number 4, which we're actually not going to completely prove because we're out of time. But what you need to know about E number 4. E number 4 simply says, let the order of A equals M, and the order of B equals to N. Then the order of AB in G cross H is what? Yes. Least common multiple of M and N. And that's something that I've been telling you guys already. they're actually asking you to prove that here. We're not going to worry so much about the proof of that as knowing that it's that way. And you can get to that because you know that the order of this element in here has to be some power, some multiple of m, and some multiple of n by theorem 5. And then you just take the smallest multiples of both of them that work. So it's not that hard of an argument to go through, but we're not really going to pursue it. What I want to do is I want to look at your homework problems. And get and this one is from chapter 10 that you're doing. And it is A number 2C. I think that's the,
2C?
which one was it?
Oh,
Oh, which one? Oh, 1B. A number 1B. Yeah. A number 1A is very straightforward. So A number 1B, there's a reason I can't see that up there.
Is this chapter 10?
Chapter 10. Mm-hmm. So what this one says is let G be a group and we're going to have A be an element in G. For this one, if m is less than 0 and n is greater than 0, show that. Did not work. Show that a to the m, a to the n is equal to a to the m plus n. So, get your hypothesis. Let G be a group, let A be an element of G. Assume that m is less than 0 and n is bigger than 0. And then what we're going to do is we're going to look at what we know. All that you're allowed to use, if you turn back to, let me tell you what page, page 103, the first 3 equations, that's all you're allowed to use for this theorem. You can't use anything else. And some of you who have come and showed me your work in my office have invariably used the theorem that you're trying to prove. So you can't use it. So all you're allowed to do is use those definitions. So let's write this down. A to the n is just going to be a times itself. Yeah, where's my little, there it is. Nope, wrong one. A times itself n times. Decoration.
Can you just like do A1, A2,
We're going to need to know the times on it. So, yeah. You can get the, yeah. If you go to insert, it says decorations right there. Alt-IC gives you decorations. Whatever letter they have underlined here, you can do Alt-I for insert and then that letter, and it will give you what you're looking for. So then, tell me about a to the minus n according, a to the m is equal to a inverse, why a inverse multiplied together? Because it's negative. And the only thing we're allowed to know is that if it has a negative power, it's the inverses that you're multiplying together. And how many times is this happening? In fact, let's actually call it the absolute value of m. It has to be a positive amount or the negative of m. negative n times. Because negative m would be bigger than 0. Now,
Or we can call it k equals like.
yeah, if you could make it k, if you want to give it a different name, you can. So let's look at this value right here. But I'm going to do one thing first. We're going to have two cases. I'll start with, consider the case that we're going to have negative m, which is a positive value, is going to be less than n, but they're all positive, so this is bigger than 0. Tell me in this case, what is n plus m or m plus n? Positive or negative? Positive. So we're going to have a to the m, a to the n is equal to, a to the m is all of these ones, a to the n is all of these ones, but now you can cancel your inverses with the a's, and you're going to have a's left over, right? Because you have a bigger n than you do an m. So we're going to have a times, well, I can just write this way. But what is going to be the value down here? I just do m plus n, right?
Could be n minus n.
I just need to know how many are left over. And if m is negative, then the difference between m and n, the number of stuff left over, is going to be n plus m. Does that make sense? So let's not put in any extra negatives if we don't have to. If you know n is positive and m is negative, and you want to know what's the difference of the absolute value of those numbers, then it's just n plus m. So what is this equal to then by our definition? Easy one. Now we're going to consider the next case. Consider the case that minus m is greater than n is greater than 0. Then what do I know about minus m and what do I know about m plus n? Less than 0, right? Yeah. M plus n is less than 0. So we're going to use the A inverses.
If n is greater, if n is positive, how come negative n?
M is negative, so minus a minus gives you plus. Suppose m was minus 4 and n was 2. You're going to have a negative number. Yeah. So notice you have minus m plus n is greater than 0, and hence in this case, I'll show you why I need this in a minute. We'll come to this. We'll just go down and look at this display. A to the m, a to the n. Cutting and pasting, we get this right here. But what is this equal to? Do we use a's or a inverses? A inverse. Just going to paste it. And what goes down here? Yeah, m plus n is negative, so we want the positive of the difference, so it would be negative m plus n, right? So what does this then become? Now, note one other thing. Yeah, note one other thing. We need to figure out what a to the m plus n is equal to. But n plus n is negative, right? So that's equal to A inverse to the negative of n plus n. So what does that tell you? These last part right here and this one are equal, so I can put those two equal. A to the n is equal to n plus n. Yeah, that is so hard because we know that rule so well. We've learned that one ever since, I don't know, it seems like elementary school. What you'll notice is that part C, they're both negative. Yeah, you only have the one case, but what you know about the both negative is, I'll just give you the hint on C. On A1C, you have m is less than 0 and n is less than 0. Oh, that did not work. Giving a to the n is equal to a inverse to the what? Negative n, which is a positive value. And negative m, which is a positive value. You can apply the rules that they already proved in the book. They proved when they're both positive. And you're going to get this right here. You're going to have A inverse. You just copy and paste this. A inverse to the n, and just add your exponents at this point. You'll have A inverse to the minus n plus a minus n. Does that make sense? Except the plus became an equals. And then you can finish. Those were the ones that I saw people stumbling on. I will be posting this later. Please correct your homework accordingly. Put it in. Okay, I'll get that posted. We are done.